So one of the greatest potential applications of crop modeling is yield forecasting. And also there are other applications including disease pest forecasting and biophenology prediction, which can potentially be utilized by stakeholders for their management decision. Timely and accurate forecasting for crop yield, disease pest risk on regional, national, and international scales is increasingly becoming important in both developing and developed countries. For example, accurate crop yield forecasting enables improved management for crop production. The farmers could adjust their agricultural management decisions to the expected climate variations to reduce adverse impacts or take advantage of favorable conditions. Or policymakers take appropriate actions to the good or poor harvest. However, most crop models are designed to simulate daily basis, and climate models like GCM have spatial and temporal resolutions. There are two cores to be used for agricultural models. The spatial-temporal scale mismatch between GCM and crop simulation models present a substantial challenge. Therefore, a bridge, in this case downscaling, is needed for linking climate information and crop models. There are two approaches for the downscaling of the GCM output to crop model level resolution. I think you guys all know about this much better than me. And considering the fact that the most dynamic downscaling requires tremendous amount of resources, for example, superpower like capacity, equipment, too much time and money will be invested. We, as an agricultural specialist, actually have no choice but to focus more on statistical method for the downscaling. So today I'd like to focus on more downscaling efforts that are taking place in our center. Okay, statistical downscaling, generally classified into three groups: weather type schemes and regression models and stochastic weather generators. These methods have been used for climate change scenario downscaling so far, and it has its own pros and cons. However, the fact of the matter here is that we do not know which method is better. I mean, which is actually appropriate for seasonal forecasting application. Downscaling was not just simple choosing one out of many type of things to us. We had to develop our own strategy. So here's our strategy for the agricultural applications of the APCC seasonal forecasting. You have a seasonal forecast from many dynamical models and also their multi-model ensemble result. In order to fill this gap between climate information and agricultural models, we try to statistically downscale the seasonal forecast in spatial and temporal formats. Many of the ideas were developed by Dr. Cho. He's not here in our department. And one of the methods for spatial downscaling was simple bias correction based on historical climate data. And moving window regression method utilizing sea level pressure or upper temperature like a T850, like a variables other than temperature and precipitation to estimate weather information for a target region. Once we get spatially downscaled and bias corrected information, which is still monthly format, so we conduct temporal downscaling with different methods. So one of which was so-called best fit sampling method, which is selecting best fit weather data from a pool of historic data or synthetic weather data. Okay, I understand from your face that you're confused what I'm talking about, but please hold that a moment. We can actually discuss that with my colleagues' help. Okay, now you have the downscaled forecast data, but you want to know whether your crop models can use the process forecast data or not, or without any problem. Since we believe some crop models are too sensitive to daily weather variations, which can be, introduced by like a weather generating process. So we can actually, let's move to here. We have to actually evaluate each crop models based on the seasonal forecast produced by the downscaling scales. So it's up to you, whether you deal with which crop models. That depends on that, decisions. Okay. At APCC, diverse approaches are taking place at the moment. Some are involved in the downscaling method and then downscaling method evaluation. And others are working with the global, regional models to develop proper downscaling method. And the others focus on temporal downscaling for their field scale models at the moment. There are also bottom-up approach research going on. So we don't need to worry about downscaling in this case, but we just use the monthly seasonal forecast information itself without any further processing. In other words, the model can utilize the monthly weather data as an input. So for this approach, currently crop models using hourly data is being converted to daily model, and daily models are converted to monthly model. Among these works, I would like to introduce some interesting researches. First, let's look at weather generator-based downscaling method and its evaluation. So this is done by Dr. Wang. Okay, weather generators are statistical models of weather variables with the statistical property they are same to observed weather climate record. There are two types of weather generators based on their modeling approach for precipitation. First one is the Markov chain approach. This is famous because of the WGen and Symmetro, something like that. And most weather generators are utilizing the WGen approach, and the spell length approach is represented by the last G, WG. So the research objective of him was to evaluate the performance of 3 weather generators called WGen and Symmetro and last WG. We analyzed for 21 stations for the daily precipitation and max mean temperature and solar radiation over South Korea. This figure shows the locations and elevations of weather stations from which the historical weather data were collected. There are 21 weather stations located in major paddy rice cultivation area. The weather generator used in this study is WGen and Symmetro and last WG. And 3 weather generators were run at 21 selected sites with 30 years observed daily weather data. For each location, 3 sets of 30 years daily time series were generated. Each data series was taken as an independent replication and used to test for significant difference between series. For each site, monthly means and variations of the number of wet days, precipitation, solar radiation, and temperature, and and blah blah, and were computed. Statistical analysis were conducted using T and F tests to determine the difference between observed and generated series with respect to mean and variation. And chi-square goodness of fit test also was used. This table shows the comparison of observed monthly means of total rainfall and standard deviation by 3 weather generators. There is no significant difference between observed data and data generated by WGen and Symmetro. But if you look at the last WG result, the amount of total rainfall observed in May is significantly large. There are 1 to 3 significant differences for standard deviation here and there between observations and WG data as well. Figure 1 shows the comparisons of observed minimum temperature with generated data by 3 weather generators. 5 stations represent 5 different topographical locations: north, west, east, and south, and low and high elevations. The performance of all three weather generators are very well in simulating the minimum temperature monthly mean. Figure 2 shows the comparison of observed maximum temperature by 3 weather generator. So synthetic data generated by last WG shows better matching with the observed one than WG and Symmetro in all 5 stations, as you can see here. Symmetro is somehow the worst one in this case. The generated maximum temperature by Symmetro are higher than the observed one in June and July. if you see here and there. Figure 3 shows the performance of 3 weather generators for simulating solar radiation. You have similar result with the max temperature result. So conclusion so far is this. The performance of WGs are good in simulating maximum and minimum temperature, solar radiation. However, they had difficulty in reproducing precipitation. The performance are different depending on the site and time period. Last WG matches the observed data better than WGN and Symmetro. Symmetro is the worst in simulating max daily temperature. And neither generator performs uniformly well in simulating the daily variations of the climate variables. As with any models, it's always important to validate the weather generator by testing it at each site before the synthetic data used in a crop model. So for this, further study should be needed to link our APCC's seasonal forecast to field scale crop model. Okay, coming back to our strategy. Sometimes we deal with a global regional scale crop model, like here. And people actually wanted to know what global outlook for crop yield looks like for this upcoming season. For large scale models, we need to take different approaches, like here. As Dr. Shin tried. At present, APCC receives 3 months and 6 months seasonal forecast data from 17 institutions around the world to develop statistical downscaling method for the global model, and thus to estimate the global scale crop yield. We use the 6-month Hindcast data from individual climate models. Here in this study, we use 6 months Hindcast data from 5 institutions, 6 climate models. This slide shows the Hindcast period of each seasonal forecast models and ensemble numbers for each individual model. Common period of 6 months. 6 models were ranged from 1983 to 2006. So we took this common period for our analysis. There are different ensemble numbers for each model, as you can see here. So we carried out single model ensemble for this common period. From 6-month Hindcast data, we can use temperature and precipitation in order to globally simulate crop model. Okay, to predict crop yield for the period of past, like this, in other words, before the time of forecasting, we can use observed daily data. And then for the future period, forecasted daily data can be used for crop models. However, since the 6-month forecast data is a monthly format, we had to downscale the monthly data to daily data. Like other field scale applications, these global scale models require grid weather data for model run. That's why we need gridded global climate data for observation and also forecast. Briefly, we had a forecast for 2014 October, let's say, which is monthly temperature and precipitation. Among historical monthly data from NCEP, the most similar year and month was selected first, and that's actually based on similarity between the given forecast and the monthly data pool of these 40 years of NCEP historical data. Once you select the closest year and month, then you can collect the corresponding daily data. Basically, through this process, we got daily scale 6 months forecast data from the NCEP historical daily data. And we can use them for model validation of utilizing seasonal forecast. Generating observed data and also downscaling seasonal forecast data requires us a series of downscaling or processes, such as bias correction and regridding and so on. For example, in order to use the NCEP reanalysis data, we do not want to use the reanalysis data itself as it is. Like Dr. Dewey said this morning, it's a similar concept to the ECMWF downscaling method. We first need to carry out the bias correction for the NCEP reanalysis data. But the problem here is that there's no counterpart for the bias correction. In other words, there is no observed real data in that same size, gridded, and daily format. That's why we had to use CRU observation data, but that's monthly. To carry out the bias correction, first we got some kind of spatial scale matching, as well as time scale matching for the NCEP and CRU data to 1 degree resolution in a monthly scale using the CDO, climate data operators. And then based on the difference or bias between NCEP and CRU, we can correct the NCEP daily data. Due to the weather variable availability from CRU data, as you can see here, only Tmax, Tmin, and precipitation can be bias corrected. But wind and solar radiation should be used without bias correction. That's the limitation we have. Assuming that the seasonal focus data also has biased, we calculated the models normally using Hindcast climatology from 1983 to 2006. Like the NCEP data, we did spatial scale matching to 1 degree using CDO to carry out bias correction of temperature and precipitation for individual models. We can simply add the models normally to the CRU climatology. Okay? Going through this whole series of processing, the seasonal focus data become properly downscaled to be used in the global scale crop model in a gridded format. So far, we discussed about a strategy to spatially and temporally downscale APCC's seasonal focus in a global grid format. Even though we are at the beginning development stage at this point, further applications using a global crop models like guys that Dr. John already mentioned in his talk is on the way. And I think the Mars system, like Dr. Dwight said in the morning, that case may be a good example to reference for this to be operational level. Okay, next strategy comes with the temporal downscaling for field crop models. Actually, this is what I'm doing right now, and weather generator based temperature downscaling was also evaluated for field scale crop model, which is a disease model in my case. And we also tried to improve its performance by introducing some additional skills and modification. Okay, this research aims to establish seasonal forecast or seasonal disease forecast, especially for rice disease. This EPIRICE is a rice disease simulation model for various rice disease. It was recently modified in order to be parameterized based on Korean field characteristics. For the seasonal disease forecast, APCC seasonal forecast information like temperature and precipitation is used as an input together with cultural practice information for that specific field. The final output could be used for control decisions by stakeholders, such as concentrated spraying over high-risk disease and pest. And based on the disease information, farmers and policymakers, they can plan for practical chemical controls for that season. However, this EPIRICE model is a field-scale disease model utilizing daily weather data. So definitely the seasonal focus data need to be downscaled spatially and also temporally. In this study, we just focused on temporal downscaling using weather generator. It was evaluated to test its applicability for the field scale crop model. First, general usability to EPIRICE disease model as a standard, a few weather generators was screened and selected for further analysis. First, you got the observed disease risk using historic weather data, which is comprised of daily rain, temperature, and relative humidity. For comparison, we trained each weather generator to be parameterized based on each specific station's weather record. And from this trained weather generator, you generated simulated weather data which were used for EPIRICE run to get simulated disease risk scores like this. So basically, you compare these to observed risk and simulated risk to evaluate each weather generator's performance. Second, we tried to improve the weather generator downscaling method by applying some additional steps. The original idea was just to modify weather generators parameter metrics based on a forecasted weather value, and then generate a series of synthetic weathers, and then use them for, EPIRICE model run. But we are not comfortable with that idea, because in that way we lose the exact forecasted value or number of given forecast. If the seasonal forecast tells 26 degrees Celsius for the next month, then the crop model should have 26 degree monthly mean temperature as an input. That's what we said. Not just a bunch of, weather generator synthesized probabilistic, weather generator, weather data. So we introduced this best fit sampling method. Instead of using weather generator synthesized data itself, we actually, use this weather data pool. So in this case, but basically, you can actually make this weather data pool more than 1,000 or 10,000. So weather generator can do that. You select the exact value of forecasted temperature based on this, and precipitation from this weather data pool using best fit sampling method. Once you select the best fit weather data, then you go through another bias correction steps to adjust the difference between forecasted data and selected best fit data. So finally, you get bias corrected best fit weather data for this EPIRICE disease model. So we selected 2 weather generators based on whether the WG generates relative humidity or not. Since the EPIRICE disease model requires relative humidity for run, this GEM was built based on US climate and WGen models, and currently it's version 6. It can generate daily precipitation temperature, solar radiation, dew point temperature, which can be converted to relative humidity and wind speed. It can, similarly, this ClimeGen is based on WGen model, and it can generate humidity and also dew point temperature and additionally evapotranspiration. Okay, this historical weather data was used from 59 ASOS, like Korean weather stations, where observed climate data from 1976 to 2005 exist. And this EPIRICE disease model was used for both rice leaf blast and rice schist blight. For evaluation, historical weather data were used to generate observed disease risk score, which is actually a simulated risk score by EPIRICE model. But in this case, we assume this one to be observed risk for the comparison purpose. Next, each weather generator was parameterized based on the same historical weather data, and then generated thousands of synthetic climate data pool for selection. In reality, we had to use the seasonal forecast data for the selection. But here, with an assumption that the seasonal forecast is exactly same to observed weather data, we used monthly averaged historical data. Basically, we ignored the seasonal forecast accuracy here in this study. We just tried to evaluate whether the temporally downscaled data generated by weather generator can be reliably used by EPIRICE model. Anyway, historical data were used to select bias-corrected best fit weather data, and the very data selected were used for model run to get simulated disease risk and compared with the observed result for evaluation. Temporal correlation coefficient and R-squared were used for evaluation purpose. Here are the first results from WG evaluation with the EPIRICE model. For this experiment, we just used 5 representative stations representing most major rice-growing region areas in Korea. As you can see here in the table, GEM showed better result than the ClimeGen for both disease model, EPIRICE LB, EPIRICE SB. Thus, we chose GEM for the next further experiment. All 59 ASOS stations and all 30 years data were used to run the EPIRICE model, as you can see here, and the observed and simulated results were compared, as shown here. Pretty good R-squared were obtained with this GEM downscaling method. This shows a sheath-blight EPIRICE model result, and you can also see relatively good R-squared for this model. There are several modifications or introduction made for the improvement of WG downscaling. As you can see here, we selected more than one best fit and run crop model with all the best fit data. In this case, 125 best fit were used for the model running, and then all resulting disease risk were averaged to get final disease risk. Comparing this 125 fit MME result with just one best fit result, you can clearly see the MME gives better result. Basically, you got many options of how many MME you want to use to improve performance. But as you can see here, 125 was the smallest with the best result. Just looking at temporal graph for one selected station data, you see the difference as well, like this. As for the EPIRICE SB, the MME similarly gives better result. Although we didn't show here, there were some modifications introduced like bias correction and relative humidity estimation, because the seasonal forecast data doesn't have relative humidity for this disease model. So we had to estimate. And many of them were contributed even a little bit more to improve the downscaling performance. Lastly, we wanted to go through this whole workflow from seasonal forecast to the crop modeling and test whether the selected crop model can generate a reliable result with this downscaled seasonal forecast data, a real APCC seasonal forecast data. Here we are showing some preliminary result using this phenology model, and so-called this is the applicability test of APCC MME seasonal forecast for using this specific crop model. Okay, this study was carried out to test the applicability of the statistically downscaled APCC MME seasonal forecast by using cherry tree phenology models, which is a simple agriculture model inputting only temperatures. So that's why we used. Simple bias correction was used as a statistical downscaling method. And seasonal forecast here, Hindcast data for model input, is composed of 3 lead time forecast data here. You actually get 3 months lead time data in January, which forecast February to April monthly temperature. When you are expecting a certain biophenological event, like a full blooming in around April, then this gives you a 3 months lead time for forecast. In the same way, the forecast data in February consists of March to May data, and it is 2 months lead time. And March forecast here has 1 month lead time for April full bloom prediction. Models used for this test were APCC MME from 11 models, and one individual model called NASA was selected for comparison. This is consists of 11 run result. There are three kinds of phenology model: dormancy clock model, development stage model, and statistical model. All models were developed to estimate blooming date of trees, but their complexity is different. The most complex one is this, and the simplest is this, statistical model. We applied these models to predict cherry blooming, and the reason why cherry was selected was because cherry is a good indicator of climate change, and it's been used a lot for that kind of purpose, I think. And also some Korean meteorological stations like 108 station have cherry trees planted inside the weather station for experimental purpose. So especially this station has a cherry blossom date record over 100 years. Here is the result. We evaluated the predictability of APCC MME forecast by comparing RMSE and SE, standard error, among different models. Here this solid star indicates APCC MME result, and solid rectangle is for NASA single model ensemble, and empty rectangles are each individual run result of the NASA model. As I said, the NASA model has the 11 run models, result. So cherry blooming date estimated from observed weather data or downscaled seasonal forecast data were compared to analyze the RMSE and SE. So this first experiment was done with the most complicated model, dormancy clock model. We know if these symbols is towards left and bottom side, the applicability of the seasonal forecast and its downscaling method gets better score. Overall, from 1 month to 3 months lead time, the cherry blooming prediction doesn't look bad. But somewhat surprisingly, the blooming date was predicted the best in this 3 months lead time forecast. We also used the development stage model for the evaluation. Likewise, the result from APCC MME and NASA single model ensemble were better at the 3 months lead time period. Finally, the simplest regression model was used, and the result looks a bit improved than those from previous two models run for both this APCC MME and NASA single model ensemble result. In most cases, 3 months lead time forecast resulted in better predictability, which is quite unusual because forecast scales normally decrease with the lead time anyway, but this is just preliminary result with one station in Korea. Thanks for listening to this long presentation first. And since I think this strategy must be continuously improved, as you all agreed, it might be good to share more time with you guys. And just going back to this strategy, in order to connect this huge gap, between climate information and this agricultural application, we still need a both-sided efforts from climate and agricultural side. As we at APCC are trying to fill this gap with all these ongoing researches and any collaboration, even with this kind of expert gathering, definitely we need some breakthroughs to get over some critical obstacles encountered at the moment. Or we may just go back to climate scientists to ask more accurate and already downscaled seasonal forecast data. But at least, as we all have been trying to so far, we need to keep trying to harden this bridge more firmly, like in our side, and stably. And also more brilliant tries should be continued while our climate scientists work really hard to improve its accuracy and reliability. Then eventually, I'm sure all our efforts will make a touchdown someday.